Hello, I'm Elizabeth Mansfield and I'm a professor at the University of Kent.
Hello, I'm Elena Celedoni and I'm a professor of mathematics at the Norwegian University of Science and Technology in Trondheim.
Hi, I'm Ari Soles and I am from the University of Cambridge.
During this semester, we are going to consider structure-preserving geometric methods for the numerical solution of ordinary and partial differential equations. And why are we concerned with preserving geometric structures? The reason is that geometric features are the natural manifestation of the physical laws. And when numerical methods preserve geometry, they perform much better than usual methods. Similarly, when we look at data analysis, sometimes structure-preserving methods can be quite useful. And the reason is, if there is some underlying geometric structure, this can be exploited in order to make sense of the data.
Yes, so there's a wide variety of different kinds of geometry and compatibility and structures that the people are concerned with. Everything from measure-preserving features to first integrals to the manifold on which the solution evolves. There's such a huge variety coming from a big variety of applications. So we are very varied in our particular research interests, but we all have one thing in common.
Differential equations historically fostered more mathematical research than any other topic, not only in differential equations per se, but many areas of mathematics, like differential geometry, topology, and so on, that have been motivated by this subject. And many really important insight has been gained historically and still being gained, with one exception, which is fundamental when it comes to applications, namely fleshing out numbers on the equations. And when it comes to fleshing out numbers, you need to compute, and this historically has been the role of numerical analysts. And typically what happened is that people concerned with structure and rigor in differential equations were not that much concerned by computation. People concerned with computation were not that much concerned with structure and rigor. And what we are trying to do is to mesh these two areas together. And the surprising thing is that both communities are responding very positively. And this gives us a great deal of hope that people will be excited, and this is the right time to talk about the subject.
So why do you think people doing numerical computation were not interested in structure? Was it because the computing facilities were not strong enough?
I think part of it, yes, and part of it is that many people, if you are computing a differential equation, more often than not, you are interested in an immediate application. Water waves or electromagnetics or whatnot. And you don't think, in a more broad sense, what does it mean mathematically? The beauty of mathematics is the same equations can explain a very wide range of phenomena, both applications-wise and mathematically.
I mean, I've come across people who really don't understand that just because their system of equations that they're solving have certain features or conservation laws, for example, that the numerics won't automatically conserve it. I mean, what do you say? I mean, when I talk to such people, I say, well, how do you know what your numerics is doing? Are you tracking it? What do you say to people who don't understand that they need to build in some of these things from the beginning?
Well, I think we need really to convey the message to two communities. To our friends, the pure mathematicians, that applications matter not only because they are very good in getting funding, but also they are very good in getting ideas. and anchoring whatever you are doing in ideas coming from applications. On the other hand, to our friends in applications, that mathematics is not simply a fancy way of explaining everything in a very sophisticated language, but actually the sophisticated tools developed by pure mathematics are incredibly powerful when it comes to applications.
We're going to address preservation of algebraic, topological, and Lie group structure. We are going to consider preservation of volume. We're going to consider moving mesh PDEs and geometric PDEs. For example, there is already a large body of work testifying the importance of preserving topological structures for finite element discretizations. And we would like to see how far-reaching these ideas are and if they can generalize to other methods and other fields. When it comes to applications, we are concerned mostly with the three types of applications. For example, plasma physics and computational general relativity and quantum mechanics.
But there are lots of other applications, aren't there?
These are just three examples.
So at the first tutorial workshop, we had Beth Wingate come and talk to us about applications in meteorology, and she made the point that the UK Met Office are now building in these kinds of geometric structures because they're finding that they cannot get the resolution that they need, even with the supercomputers that they have. They're driven to the point that they, in order to achieve the level of prediction that they need with the data that they have, they're forced to use geometric preserving algorithms.
Yeah, so we have already mentioned the three applications, and let me finesse it a little bit. So when it comes to plasma physics, we know, and plasma physics is incredibly important in a range of areas, from astrophysics to the design of fusion reactors. And these are fiendishly complicated equations. But these are also equations that have very well-defined structure. And in the last few years, especially people concerned with fusion physics have realized how important it is to maintain this structure. And this is not an easy exercise, but this is something with huge potential and huge importance. In general relativity, there are difficult nonlinear equations, the Einstein equations and so on, equations concerned with black holes, and somehow in the last 20, 30 years, there have been a major disconnect between people in general relativity and people in numerical analysis. And now we wish to repair this disconnect, to bring these two communities together, to use these modern tools that are available to us now and try to generate a common agenda to the two communities. When it comes to quantum mechanics, again, these are very complicated equations. They exhibit a range of phenomena, preservation of various types of structure, high oscillation, and so on. And again, in the last few years, we have started to develop methods that are by orders of magnitude better, and they are better because they can preserve structure.
Do you think it's fair to say that people have been working on structure preservation for a while and there's a basic understanding for simple problems, and it's really now time to move on to the bigger, meatier problems?
Yeah, now, when you look back in history, the first person to design a numerical method that preserved structure was a certain Isaac Newton.
Yes, he did. Yes.
So, of course, these ideas have been around, but only in the last 20 years or so, we have started as a community to address them in a methodical fashion.
I think it's fair to say it was a real surprise to find that symplectic integrator in the Newton's Principia. Did people realise that was a symplectic integrator?
Well, the person that was the first to realize it
Yes.
was Richard Feynman.
Oh.
Yes. So even the realization has incredibly impressive pedigree.
That's right. Well, there's going to be another program starting in September on applied complex analysis, and one of the main themes of that program are the Palavey equations, and these are completely wonderful and magical ordinary differential equations which were discovered about 100 years ago or so, I guess.
Yes.
Whose solutions have a very particular pure mathematical property. But in the interim, it's in recent years there are an enormous number of applications of these, and these particular ODEs and their solutions have marvellous structural properties that come from the fact that they are reductions of integrable systems such as the quarter vector Breeze equation, and ultimately they come from the Self-Yang-Mills equations. There's a lot of Lie algebras, there's tremendous structure in the details of them, and huge, I can't begin to tell you how many how many papers have been written on the Palavey equations and their applications. And so these are going to be of particular interest to you and me, and they have marvellous, they're an opportunity in waiting for people with our kinds of skills.
Well, let me go further. So, I think it was Jacques Hadamard who said that the shortest path joining two real points goes through the complex plane. And at least in my experience, whenever I do research, somehow, at the end of the day, I end up with problems in complex analysis. And I'm really looking forward to collaboration with these people, not only on Painlevé, but on a range of other problems, including problems that originated in structure preservation, but really require complex analytic tools. And we are already talking with organizers of the other program about a joint agenda. So I think that the setting of Isaac Newton Institute will be very conducive to generalizing this sort of agenda.
On a different note, I would like to mention that we are also quite interested in problems of data analysis and image processing, and we have already had a number of talks in these topics, and we are all aware of the importance of deep learning, and we are trying to understand a little bit more of that.
So are there differential equations in deep learning?
Absolutely.
Of course.
There are a number of ways of interpreting deep learning, but one of them is deep learning as optimal control problems, and then both PDEs and ODEs are really important.
So what kind of structures do those equations have?
Well, there is a Hamiltonian structure, but it's not very well understood what kind of ODEs you should really use to model properly deep learning.
Well, the truth of the matter is that we know that deep learning works. We don't know why. There is no mathematics. There are hundreds of people trying to construct mathematical foundations. And personally, I'll be incredibly surprised had differential equations not played fundamental role in understanding it, eventually.
Eventually, yes.